Hello everyone. In this video, I'm going to explain, based on entropy, why under certain conditions water freezes while it failed to freeze under other conditions. So but the basic thing here that we want to deal with is just entropy. Now, based on entropy, we know that there is a disorder between particles of matter. And using entropy, we can measure the degree of this disorder. Now, we want to apply the principle of thermodynamicness and the kinetic stability of certain reactions to understand why, under certain condition, water can be found as ice, while in other conditions, it is always found in liquid form. Now, at one side, I'm going to have ice. On the other side, I'm going to have liquid water. Now, the first thing that we have all agree here is that liquid water has lower entropy. Sorry, ice has a lower entropy and liquid water has a higher entropy compared to ice. But since the conversion of liquid water to ice is exothermic, the reaction is exothermic, so meaning the delta S of the surrounding will be positive under standard conditions. Now, it doesn't necessarily be that it must happen under standard conditions, but we can pick it that way. But for this reason, because the reaction is happening at a temperature below zero, that's when we can find ice. I'm assuming that the reaction is happening under non-standard conditions. Now, since the reaction is exothermic, entropy of the surrounding will be positive. But initially I said that for entropy of the surrounding to be positive, it means that its magnitude is greater than entropy of the system. So, for that matter, I can make a conclusion. That for water to freeze, entropy of the surrounding should be greater in magnitude than entropy of the system. This one will give us entropy total that is positive. It is this that will make water to freeze. So, I wanted to imagine two scenarios. I'm having a scenario. Let me pick a plane in which I'm having a line here drawn. The middle part is 0 I have -1, -2, -3, -4, lastly -5. Here I'm having 1, 2, 3, 4, and 5. It is always said that water freezes at 0 when pure, at 0 degrees when pure. So I'm going to treat these ones as degrees Celsius. So at 0, water will start freezing, meaning it is changing from liquid to solid. So I can have two scenarios. For example, I want to determine if really what is causing water to freeze at a temperature of -5, and also what is causing water to be a liquid at a temperature of +5 degrees Celsius, respectively. So I'm going to divide this space into two. Then I'm going to do my calculations. So let us see what we are going to have at the end of the day. So imagine this reaction. Imagine this reaction. I'm having H2O, that is a liquid, changing state to H2O, that is a solid. And I'm told that delta H for this given reaction is exothermic and 6010 joules per mole of energy is lost. And for that same reaction, I'm told that entropy under standard conditions for water is equal to 69.9 joules per Kelvin per mole. The same entropy under standard conditions for ice is equal to 47.9 joules per Kelvin per mole. So I want to justify what is really happening at different degrees. So the justification I'm going to give here will be at +5 degrees Celsius, which is also the same as 5 plus 273 Kelvin. So delta S of the system is going to be that of the products minus reactants. So if you look at that chemical reaction that is, or chemical change that is occurring there, I'm having a liquid forming a solid. So it means that my solid is the product here. So I'm going to have summation of entropy of ice minus summation entropy of liquid. So it means that I'm going to have a situation whereby delta S of the system is going to be delta S of the system is going to be 47.9 minus 69.9. If you do your calculations very well, you're going to get 22.0 joules per Kelvin per mole. But for the surrounding, we know the formula is negative delta H all over temperature. This is where now we need the temperature. So I'm going to have negative of negative 6010 all over 278 Kelvin. When you do your calculations very well, you're going to get 21.6 joules per mole per Kelvin. So meaning, if I'm to calculate my delta S total for that given reaction, this is going to be delta S of the system it's going to be delta S of the system plus delta S of the surrounding. So at the end of the day, my delta S total is going to be negative 0.4 according to my calculation joules per Kelvin per mole. If that's the answer I'm getting, what does this denote? At that temperature, which is positive 5 degrees Celsius or 278 Kelvin, will water be a solid or a liquid? So, in conclusion, we can say total entropy change is negative. Is negative. You are getting a negative value. Meaning, this change is not thermodynamically. It is not thermodynamically feasible. For that reason, water will not freeze. So, it will still be in liquid. So, if you look at our calculation very well, we want to follow the same calculation, but now we want to see what is going to happen at a temperature of negative 5. So, at negative 5 degrees Celsius, or we are going to take Kelvin 273 minus 5. What will happen? At this, we are going to start with the delta S of the system, which is going to be the reverse of what we did. But because the system is the same, it's still changing from liquid. So I'm going to have still 47.9 minus 69.9. And the value I'm going to get here, just minus 22.0 joules per Kelvin per mole. But delta S for the surrounding is going to be negative delta H over temperature. After doing the subtraction, what are we going to have? I'm going to have negative of negative 60 10, sorry, 60 10 over 268. So this one is going to give me plus 22.4 joules per Kelvin per mole if you do your calculation correctly. And delta S total for that given reaction at that temperature is going to be positive 0.4 joules per Kelvin per mole. So because we found a positive change, what can we say? The total entropy change is positive. Is positive. What does this one mean? That the change is thermodynamically spontaneous. The change is thermodynamically spontaneous.